Example 3 is going to use a formula that they don't give you any questions on in the workbook, which is one of the reasons why I've also included some supplementary practice at the end of the lesson, is to give you some practice using this other formula. The instant you're given the angles and you're asked to find the corresponding wavelengths of the X-ray coming in and the X-ray exiting, then you're going to need to use this other formula on your sheet. Again, it's up in the quantum mechanics and nuclear physics section. It's the change in wavelength formula. So let's list what we know. We have a wavelength coming in, so I'm just going to write it as wavelength initial, 1.24 times 10 to the negative 11 meters. Hits a section of foil metal, and it's got a scattering angle of 40 degrees. Calculate the wavelength, so we're looking for the final wavelength of the scattered X-ray photon. So this is the example that I was showing some diagrams in there. The X-ray comes in, hits the electron moves off at some angle, the photon, X-ray, moves off at some angle. It's as a result of its losing some energy, and then as a result a longer wavelength is what's giving the particle nature of light. So this formula, the change in wavelength formula, equals h over mc times 1 minus cos theta. H, we know, mass is the mass of the electron it's in contact with. C is speed of light. Theta is the angle of the scattered X-ray, and we have that. So we have everything in here to find change in lambda. So the change in wavelength will be equal to, again, 6.63 times 10 to the negative 34 joule seconds divided by 9.11 times 10 to the negative 31 kilograms, mass of an electron, off my data sheet, 3.0 times 10 to the 8 meters per second, and we're going to multiply this by 1 minus cosine 40 degrees. I might want to punch in the h over mc first, 6.63 to the exponent negative 34 divided by 9.11 exponent negative 31 times 3 to the exponent 8. Work out that number, then multiply it by 1 minus cos 40 degrees, and we should end up here with, I think I've got the wrong mode on my calculator, and I do. We should end up here with 1.36. Oh, wait. Sorry, one more time. I got to punch this in. Second function exponent negative 34 divided by 9.11 exponent negative 31, 3 to the exponent 8 times bracket 1 minus cos 40. You end up with a change in lambda, this isn't the answer, equal to 5.676 times 10 to the negative 13 meters. You're not going to see a lot of change. Maybe to your third sig dig you will see a change. Now, change in lambda is going to equal to the final wavelength subtract initial wavelength. So what we want to do is find the final wavelength equals the change in lambda plus the initial wavelength. And if we punch that in, so keep your original number on your calculator so you're as accurate as possible, add the initial wavelength, 1.24 times 10 to the negative 11 meters, and your final wavelength equals 1.296, which I guess if we go to 3 sig digs, 1.30 times 10 to the negative 11 meters. That should make sense. The wavelength gets longer upon scattering. 1.30 bigger than 1.24. So you come in with a very short wavelength, loses some energy. As a result of losing energy, it has a longer wavelength. And it won't be a significant change. It'll be a very small change, like what you see here. So that's one example using the scattered X-ray formula. And there's lots of this practice in the supplement practice that I've given you in your notes. There isn't any in the workbook, so you need to practice this one.